Tēnā tātou I te whare. Tūtaua mai I runga, tūtaua mai I raro, tūtaua mai I roto, tūtaua mai I wao. Kia tau ai, te mauri tū, te mauri ora, ki te katoa, haumie hui e, tae ki e. Good evening everyone and welcome. Following our opening karakia, I would like to welcome you to the National Museum of New Zealand Te Papa Tongarewa. Kei aku nui, kei aku rahi, kei aku rangatira, tēnā koutou katoa. Nau mai haere mai ki te whare pūpuritanga o te Papa Tongarewa. Haere mai koutou I te kaupapa kōrero o whakaruāmoko, nō reira tēnā koutou katoa. My name is Kat and I am one of the public programming team who've had the pleasure of working with the team at the Natural Hazards Commission Tokatu Ake to put on the Active Land series of talks. This is the second out of 3 talks this evening, and my role is very brief. I'm just here to welcome you and to do the housekeeping. Then I'll be passing over to our fantastic speakers. So let me move into that. Wharepaku, if anyone needs the toilet at any point, please head to the back of the room and round the pounamu. We've got some toilets over down the corridor. In the unlikely event of an emergency, please follow the guidance of our host team. They're wearing the event t-shirts at the back. They're waving at the moment. Please turn your phones on to silent. Turn off any alarms if you haven't already. You're welcome to take photographs, but please turn off the flash. This event is being live streamed and will be recorded for you to access online afterwards. So kia ora to our online audiences this evening. You will have the opportunity to ask questions as well, so just put those in the chat. One of our team members is monitoring that for you. And that's it. I'm going to hand it over now. I'm very excited to introduce this evening's talk, Building Wellington's Earthquake Resilience Together. This is the second, as I said, of our 3 talks, and it's going to be facilitated by fantastic Dr. Natalie Balfour. We've got 4 speakers here this evening, and I would invite you to warmly welcome them. We've got Dr. Nicola Litchfield, Dr. Kate Clark, Dr. Shenlin Ling, and Dr. William Power. Thank you very much.
Thank you, Kat. Tēnā koutou katoa. Welcome to this Kōrero Whakaruamoko Active Land Talk, the second in the 3-part series. I'm Natalie Balfour, Head of Research at the Natural Hazards Commission, Tokatu Ake. As a seismologist, I'm especially excited to be hosting the talk tonight, which is all about the awesome forces that shape the Wellington region. It's a topic that's front of mind to many of us here in Wellington, where our beautiful scenery and frequent rumbles are a constant reminder that we're living on active land. It is also front of mind to us at the Natural Hazards Commission, where our mission is to reduce the impact of natural hazards like earthquakes on people, property, and the community. An important way to do this is by investing in research and modelling like the kind you'll hear about this evening. And it will help us better understand the natural hazards we live with and how to prepare for them. Together with Te Papa, we launched this Active Land Talk series to showcase some of the best examples of how science is being used to inform resilience to natural hazards. Tonight we'll hear from the scientists from the It's Our Fault research program. Apart from the name, what's also brilliant about this research program is that it's all about teamwork. Firstly, teamwork between the scientists from different places who work on kind of the same thing in different ways to better understand Wellington's earthquake risk. Secondly, it's about teamwork between the scientists and the communities. And in fact, it's a fantastic example of boots on the ground science. That It's Our Fault scientists work with the local council and emergency management to make sure that they understand the challenges that we face when it comes to earthquake resilience and how scientists can be used to solve some of those challenges. It's no wonder this is an award-winning program and one of the longest running research programs in New Zealand. We're really lucky to hear about it tonight. So tonight I'll begin by introducing each speaker, who will share their mahi for 10 minutes. After each has spoken, We'll have a Q&A session where you'll get the chance to ask our speakers some questions. So please hold on to your questions until the end, maybe make a note, and we'll get started. So first tonight, we'll hear from Dr. Nicola Litchfield. Nicola is the science leader for It's Our Fault. She's also a principal scientist and a paleoseismologist at Genius Science. Her specialty is studying past earthquakes and how they've shaped our landscape and what they can tell us about our future risk. Please join me in welcoming Nicola.
Thank you everyone for coming. We're very excited to share this with you tonight. And before I forget, I need to make sure we thank our sponsors. So the It's Our Fault program is bringing you this talk tonight. We are going to tell you information that's been gathered in a number of programs that we bring together through the It's Our Fault program, but the It's Our Fault program is funded by the Natural Hazards Commission, Tokatuake, Wellington City Council and REMO, the Wellington Regional Emergency Management Office. That's all the emergency managers. This is the order of the talks. We're changing it slightly from what was in the program, so I'm going to give a sort of a high-level latest research on a number of hazards in the program, and then Kate and William are going to give you much more information on two of the big hazards, the Hikurangi subduction zone and tsunamis. And then Shinglin's going to give an example of our working with communities, and this is a pilot study we did with a Māori community in Porirua. So, as Natalie mentioned, it's one of the longest running programs, certainly at GNS. It started in 2006, and since then the vision hasn't changed. It's to make the Wellington region more resilient to earthquakes and related hazards. And just a couple of points there, it is the whole region, but sometimes we do stray outside the region too, because the faults don't stop at the region and so on. You'll hear a bit more about that. It is, focused on earthquakes and all the related hazards, so it's not storms and flooding and things like that. So starting off with active faults, I think we all know we have lots of active faults in the Wellington region, and throughout this program we've mapped lots of them, and we are unfortunately finding more all the time as we get better data sets. So up on the top right you can see a summary map. We have faults onshore and offshore. So some of the findings, this was an early one in the program, but it still holds true, is that the Wellington Fault earthquake is not overdue. For a long time we're always going on about the Wellington Fault being overdue, and we found through our research, we were digging trenches like the one in the bottom, we found that the most recent earthquake was more recent than we thought, and that they happen less frequently than we thought, so that's a good thing. And we've started working on a bunch of other faults as well, and so far we've come up with probabilities of large earthquakes in the next 50 years that you can see here. So the Wellington Fault's not zero, it's not gone away, but it is around 5% chance of a Wellington Fault, a big earthquake in the next 50 years. As compared to the Oharu Fault, which goes through Oharu Valley, Porirua, up to Transmission Gully, it's about 2%. And the Wairarapa Fault over on the eastern side of the Remataka is only 1%. That's a very big fault, but it ruptured in 1855, so it's not due to have another one for a while. As I mentioned, we are finding more. Another hot topic at the moment is vertical land movements, particularly around the coast in the light of sea level rise. We know that from our GPS stations, the GeoNet network and things, and the tide gauges, that in general the Wellington region has been sinking slowly over the last 2 decades or so that we've been measuring. It's been going on longer than that, but we can see that really clearly. However, that's just what's happening now, and we know that that's in part because of the Hikurangi subduction zone that Kate's going to talk more about. But as I mentioned, lots of active faults, and we know from things like the Wairarapa earthquake in 1855 that uplifted, this is Te Rākarai Head looking back towards Bearing Head in the city, and we know it uplifted all that area in 1855, gave us a road to drive out to the heart and places. But I think you probably also know that here and places like Petone are on the downside of the Wellington Fault, so it will drop. So we're trying to get a handle on which ones are going to go up and which ones are going to go down, and Kate has had a student looking at modelling faults, all these white ones here, and trying to figure out which ones are going to go up next and which ones are going to go down, and it is complicated, and generally we're finding The Wairarapa tends to go up more than down, but as I mentioned, in the Wellington city area, it's tending to go down, but sometimes it might go up. So it's complicated, but we're working on this, and we're working with other programs to incorporate those into sea level rise forecasts. Another hazard you might not think about in the context of earthquakes is fire. But when you stop and think about it, we have a lot of earthquakes, obviously, but we also have a lot of reticulated gas in the city, wind, closely spaced wooden buildings, steep slopes, vegetation. So this is one. I mean, we do know fires happen after earthquakes. They happened after Napier, 1931, San Francisco, 1908, which has similar kind of hills and buildings and stuff to us. So we've been modelling this over a few years in the program, and yeah, it's quite regional scale. It doesn't get down to individual houses, but we have managed to look at some of the areas that are more vulnerable than others, and then feeding this to FENS to help when they're buying new equipment and prioritising where it goes and things, to consider the earthquake fire risk. Landslides. We know we have lots of landslides in Wellington. They happen all the time in storms, but I guess it's no surprise that they also happen in earthquakes. So most of the landslides in the database here are actually from storms. Some will be from the Kaikoura earthquake and the Wairarapa earthquake. So we've been building databases. We've been looking at what's beneath our feet, what's the land like. In particular, one of the things that we know as well is that because we've got lots of steep slopes and lots of roads, we've cut a lot of road cuttings to make our roads, and we've filled in areas to make areas to build on, and they are a little susceptible to landslides, so we're trying to get a handle on that, and pulling together other information like the geology, the slope and so on, we can start getting a handle on landslide probabilities. And this is a map on the right, just one model for a Wellington fault earthquake, and you can see maybe the red areas that light up along the Wellington fault, not surprising, steep slopes, but there are other areas, particularly around the coast where the coast is very steep, that also might have landslides in a Wellington fault earthquake. Ground deformation, this could include landslides, but what we can do these days, we've got satellite data. The satellites are passing over all the time, and this particular data set here is a satellite that passes over every 6 to 12 days. And so that actually allows us to monitor how the land is deforming. We're actually getting data down to, I think it's 6 by 13 metres, so sort of, big building size. So we really can get detailed information about what the land's doing, and then they do this thing called fancy INSAR analysis, which basically looks at the difference between two satellite images, and they look at vegetation types, and then pull it into clusters to look at areas that are going up and down hotspots, and that's what this map on the right here. And this map is actually an area of what's called apparent subsidence. Basically, it means that the land is going down relative to the satellite, and you can see some hotspot areas that perhaps aren't surprising, reclaimed land around the port. We know that subsided in the Kaikoura earthquake. Fill bodies, I've mentioned before, we've sort of put all this fill in, perhaps times haven't packed it down. Oh, I should mention, Te Hapa doesn't light up here, so they've done a good job compacting the land around here, so that's good. Quarries, we can actually see actual quarrying. I think that's probably the Kiwi Point one up here, but interestingly, even the Mahero, is that the name of it? The one down on the south coast is also apparently going down, even though it's not active anymore, so that's one to watch. Recent construction zones, we can see houses going up and buildings going down, being pulled down. But also, interestingly, sometimes after buildings are built, the land appears to settle or sink as well. So we can see that. So anyway, this is a great way to monitor what's happening around the region. And I'm almost finished. So the other things we do is these kind of talks. We run workshops. The top one is the one that we run every year. We run workshops for planners to get them informed of the latest hazards research and how they can use that in their planning. We run a thing called the Wellington Earthquake Resilience Collaboratory, which is just trying to bring everyone together, because there's lots of people working on earthquake resilience in Wellington, which is great, but getting everyone working together so that we're not duplicating efforts and so on, pooling our resources, and contribute to other things like science festivals. And my final slide is just to say, if you want to know more about the program and some of the things I've talked to you very briefly about today, is go to our website, it's ourfault.org.nz, and you can actually download all the reports, all the work that we've done for free. It's a policy of the program. So yeah, I'd encourage you to do that. And I'm going to hand over to Kate. Thank you.
So thanks, Nicola. That was a great overview of the research program and lots of morsels and nuggets of some of the things that you've been working on. Now we'll hear from Dr. Kate Clark. Kate leads the paleoseismology team at GNS Science, where her work has been critical in helping us understand the hazard posed by some of our largest fault lines in New Zealand, such as the Alpine Fault and the Hikurangi subduction zone. Welcome, Kate.
Thank you, Natalie, and thank you for everyone coming out tonight to listen to this. So yeah, I'll be talking about the Hikurangi subduction zone. Just to start off with the real basics of a subduction zone. A subduction zone is where two tectonic plates are colliding and one is being pushed underneath the other or subducted beneath one. So Wellington lies above the Hikurangi subduction zone, which is where the Pacific plate is being pushed underneath the Australian plate. So we're on the Australian plate here. And the subduction zone is about 20 kilometres beneath our feet. So there's several sort of components to a subduction zone. I'm just going to run through a few here. If we sort of went out to Cook Strait and cut through the earth, you'd see something, this is a pretty cartoony version of it, but something like this. When I'm talking about the subduction zone or the subduction interface, I'm talking about that boundary that's dipping sort of from the east coast towards the west coast, getting deeper as it heads towards the, hang on, did I get that the wrong way around? From the east coast to the west coast. Dipping deeper as it goes further to the west. And yeah, where we are here, it's about 20 kilometres deep. So the subduction interface and the earthquakes that I'll be talking about are on that plate boundary at depth beneath our feet. Running through the Australian plate, the plate that we're on, is all these other active faults. These are called upper plate faults or crustal faults. So they're things like the Wellington fault, the Weighted Upper fault, some of the faults that Nicola mentioned. Still really significant faults, and it's kind of the subduction zone beneath it all is kind of the engine driving all this tectonic deformation. So they're related. And both upper plate faults and the subduction zone can produce large earthquakes, but the very largest earthquakes occur on the subduction zone. So it has the potential to host the largest earthquakes. And what is particularly significant, what William will talk more about, is that subduction zone earthquakes have a really high potential to produce large tsunamis, because when there is a big earthquake, it moves a significant amount of the seafloor. So how we sort of monitor what's happening on the subduction zone today is largely through using really sensitive GPS instruments to monitor ground deformation and seismic instruments. And this map up there, those colours are sort of showing through mainly GPS monitoring how stuck together the two tectonic plates are on that subduction interface. So yeah, it's kind of a map of how sticky things are, and where things are more stuck together, you've got the stress building up that will eventually be released in a large earthquake. And unfortunately, we're on that bright sort of yellow hotspot where the plates are very much stuck together, sort of in a locked zone. So the plate interface, the two plates beneath us, are stuck together currently. There have been no large subduction earthquakes on the subduction interface during written sort of European histories in Aotearoa. So how we try and understand the future or the sort of potential for these large earthquakes to occur in the future is through using the geological record. And here's a little cartoon that's going to play that sort of shows an animation of a subduction zone earthquake. So you've got those plates being locked together, a large earthquake, you have the seafloor moving, it produces a tsunami, and after an earthquake, some of the land that was going down before will pop up, and some of the land that was going up will subside. So you get land movement and a tsunami. The other major impacts at the time of the earthquake is widespread ground shaking and, of course, landslides. But as a coastal geologist, the things that I use to detect these past earthquakes is that vertical land movement, so where the coast has gone up or down, and the tsunamis. So we use these sort of geological signals to tell us how often, where, and if we're good at our jobs, we can try and detect how big these past earthquakes were. And this is used to forecast the future impacts from these types of earthquakes. So on the southern Hikurangi subduction zone, where we are at the moment, and we do work right along the Hikurangi subduction zone, but I'm going to focus on the southern zone here, we've worked on a number of sites. So we've got several in the South Island, sort of bordering Cook Strait, and many in the lower North Island. The two key sites that I'll talk to start with are those ones in Marlborough, so the Wairau Lagoons and Kapara Tahoe Lake Grasmere. So the Wairau Lagoons are over near Blenheim. There's, you can see Blenheim sort of right in the background of that top photo, and that's a photo of us on the bottom collecting some sediment cores from that lagoon. These big, shallow coastal lagoons, they're really excellent sort of geological recorders of past earthquakes and tsunamis, because the sediments and the little fossils, shells, sediments, they record changes in sea level. They're very sensitive to changes in sea level, and also sort of preserve tsunami deposits. So what we've found through this work from collecting sediment cores at numerous places around these lagoons, we could see that the land has dropped suddenly, like almost sort of very rapidly, at 2 times in the last 1,000 years, so one at about 500 years ago and one at about 850 years ago. And you can see those core photos there at the bottom that show what that change looks like in a sediment core. And we can see also from this core sand layer in one of those photos that the earthquake, where it all dropped suddenly at 850 years ago, was accompanied by quite a large tsunami. And our modelling suggests the only really viable source of earthquake to cause the land at this point to drop suddenly is an earthquake on the subduction zone. Going further along the Marlborough coast, we've worked here at Lake Grasmere, where the saltworks is in the upper South Island. So again, that's this large coastal lagoon with a low barrier. It's a really ideal site for preserving tsunami sediments. So when a tsunami washes in from the open bay here, it carries marine sediment, washes over that barrier, and it's deposited in this quiet environment behind there in the lagoon. And again, there's some photos of what some of the sediment cores from the northern edges of Lake Grasmere look like. And we found here 2 really extensive shell hash layers, spelled shell wrong there, 2 really extensive shell layers across the northern side of that lagoon. And these have all the characteristics of a tsunami. So shells that were washed in from the open bay, pushed over the barrier and spread out in this big, quiet subtidal lagoon behind and preserved there. And we can radiocarbon date those shells, and they're about one layer, the older one is about 2,000 years ago, was deposited then, and another layer was deposited about 1,400 years ago. And we can use tsunami inundation models to try and match the extent of that tsunami layer with where the tsunami might have come from. And again, we see the most compatible source is a large subduction earthquake on the southern Hikurangi subduction margin. We don't see land level change at this site, which might just be because that subtidal lagoon is not very sensitive at recording small changes in sea level, or it might be that at this site it wasn't accompanied by land level change. Moving on to the lower North Island here. This is out here, Pukamori Stream, out near Tora on the Wairarapa coast. And when you look at the LiDAR, the high resolution topography of that site, you see sort of these bathtub rings along the coastline. So these are former beaches, and each of them represents uplift in a past earthquake. So at this site, we've got this really nice archive of seven marine terraces representing 7 past earthquakes. And we can go to these sites and collect sediments and try and date when those earthquakes occur and measure how much the coast uplifted each time. Here's another site. This is a site led by Nicola. Similarly, at Cape Palliser here, we've got these steps around the coastline. Each one represents past earthquake. And she collected shells from some pits on the lower terrace here and dated that earthquake there that uplifted that beach at about 860 to 560 years ago. So that overlaps with one of those earthquakes that we saw at the Wairau Lagoon, giving us some sort of hints at perhaps the extent of these past earthquakes. Our most recent site is Lake Kohanga-Periperi, which is out near Pencarrow Head, out at the entrance to Wellington Harbour. And we only just collected cores there in June, 2 months ago, so really fresh research there. We're analysing them at the moment to see if we can detect a record of tsunamis that have inundated this lake or potentially land level change associated with past earthquakes. And I just wanted to acknowledge there the immense help and support we've had from Taranaki Whanui and their Roputiaki Management Group in Greater Wellington to enable us to get out there and collect those sediment cores. So in these past earthquakes, and I've mentioned 4 different dates now, so if we sort of put that together with a bit of information we have from many other sites around the lower North Island and up the east coast, we're starting to see this record of when subduction earthquakes have affected the lower North Island and upper South Island. So we see a fairly regular pattern of an earthquake about every 500 years ago, since 2,000 years ago. All of these are likely subduction earthquakes, so we have a recurrence interval of about 500 years with a bit of variability there. This record of past earthquakes allows us to then forecast when a future one might occur, and we've calculated from that there's a 26% likelihood of another one of these large subduction earthquakes in the next 50 years. To sort of put that, so Nicola mentioned the Wellington Fault, probability there of 5%. The Alpine Fault has a probability of about 75% of a magnitude 8 earthquake in the next 50 years. So just putting the sort of subduction zone, 26% is a pretty high number. Alpine Fault, quite a lot higher. At the moment, our subduction earthquake work through It's Our Fault and a few other projects at GNS, we're really focused on working on sites closer to Wellington City so that we can better forecast the impacts to our city and the suburbs around us. We're currently working on that Lake Kohanga-Periperi site and also compiling that work from Wairau Lagoons and Pukemerri Stream. And our aims with all these new sites is to improve the record that we've already got. So it's a start, it's not a perfect record. We want to extend that record back in time. So when I was talking about that number from the Alpine Fault earthquake record is 8,000 years long, and we have a record of 24 earthquakes. So the longer and more accurate our past earthquake record is, the better we can forecast the future likelihoods. We're trying to better understand tsunami impacts, understand the land level changes associated with these earthquakes, really understand the timing better, and we're also trying to look at whether the subduction zone ruptures at the same time or in close sort of sequence with upper plate faults like the Wellington Fault or the Oharu Fault. So that's the summary of our subduction earthquake work. Thank you.
Thanks, Kate. It's just amazing to see what we can learn from the environment that happened so long ago. It's really cool. Next we have Dr. William Power. William is a senior geophysicist at GNS Science and an expert in all things tsunami. He develops models to assess tsunami hazard, and he's one of the experts that the government will call on for advice in the event of tsunami. So welcome, William.
Thank you, Natalie, and good evening, everybody. So I'm going to talk about tsunamis in Wellington Harbour. Kate has already done a reasonable job, well, a very good job of setting, pardon me, of setting the scene here. So here we are on the boundary between the two tectonic plates, as Kate has shown. And this is a sort of a cross-section of how this looks through the Wellington region. We have the two plates passing, the Pacific plate passing under the Australian plate. This is the boundary between the two. And here are various, what we call, well, faults that branch off from the plate interface and come up to the surface. And these are the faults that we're most familiar with, like the Wairarapa fault, the Wellington fault, the Hario fault. So we see them cutting across the landscape, but they actually are surfaces that sort of dip down beneath us and connect to this subduction boundary. So the tsunamis that we're most concerned about are those generated on the subduction interface, but we also can have tsunamis generated by these other faults. In terms of thinking about tsunamis in Wellington Harbour, it's appropriate to start off by talking about the most significant historical tsunami that we had in the harbour, which was the one that occurred in 1855 when we had the Wairarapa fault earthquake, which was around about magnitude around 8.2 perhaps. And that was a very long rupture that sort of started up far in the Wairarapa, came down through to the south to around Te Whanganui-a-Tara Head and out into Cook Strait. And around where it came to the ocean, there was uplift of several meters. And our understanding is that that uplift extended offshore, so the seabed is also was also risen several meters probably in this area at that time. And as you saw on the animation in Kate's talk, the movement of the seabed raises the water up above it, and that's the initiation of the tsunami. These bars are showing the maximum sort of observed run-up height, so how high the water got to above the normal level. So the highest run-ups in 1855, up to about 10 meters, were on the South Wairarapa coast. There are quite large run-ups also in the Marlborough area. Closer to Wellington, we think at least 4 meters around the south coast of Wellington. So our understanding is that the tsunami crossed the area between Lyall Bay and Evans Bay, probably in both directions. So the earthquake occurred in the evening, so it just about got dark. And at that time, people didn't actually live in that area between Lyall Bay and Evans Bay. It was an area of sand dunes and flax and toi, and people would pass through going to and from the Miramar Peninsula, but it wasn't inhabited. The reports talk about the water coming to about 3 feet of height over the dunes, and the next day, many people reported fish that were sort of stranded amongst the flax and the toi, which is a pretty classic sign of a tsunami. There'd also been a small boat that had started off at Evans Bay and had been found a day or so later in Lyall Bay. And that's kind of interesting because that suggests that as well as we probably both had waves coming from Lyall Bay into Evans Bay, but probably also had some waves that were crossing in the other direction to move that boat across. Inside Wellington Harbour, our best estimate is that the run-up heights go to about 2 meters. This is a view of Lambton Quay, taken in 1860. Back in 1855, this really was a quay front. So this would have been, there would be wharfs coming off from here where small ships would dock and they'd bring their cargo in and out of the buildings on the quay. And very shortly after that earthquake, in fact, a series of waves came and washed in and out of those quay houses, so causing quite a lot of panic, quite a bit of disruption. Nobody was seriously hurt, fortunately. It's interesting that the first waves are reported to have come very shortly after the earthquake, which suggests that they were probably, the first waves are probably what they call seiche waves. So seiching is like the sloshing in a bathtub. So as the whole harbour is moved side to side, backwards and forwards in the earthquake, that can cause the water to slosh backwards and forwards. And because those first waves arrived very quickly after, we suspect they were from this seiching effect. And the subsequent waves that came on for many hours later were the tsunami that had come in through the entrance from Cook Strait and was circulating in the harbour. Something else to see in this photo, I mean, this is 5 years later, and you can see what was the quay front is now somewhat high and dry, because the whole area was uplifted by perhaps 1.5 meters, 2 meters or so. So this area in front eventually, you could no longer bring your small ship up to dock here, was eventually reclaimed, and that's now what is now the Wellington Central Business District. Okay. Okay. Point that way? Oh, yeah. So this is an animation of a computer model of what could happen in a magnitude 8.9 Hikurangi subduction zone earthquake and the tsunami that follows it. So the different colors are showing the heights of the waves. So the sort of red colors are positive and the blue are negative. And we have, in this particular model, we have an earthquake that extends up from Cook Strait up towards Hawke's Bay. We see waves very quickly come along the Wairarapa coast, but then also come to Wellington Harbour and wrap around to places like Pororua. The first waves getting to the Wellington south coast after only about 10 minutes. We see the inundation of this area around the airport, similar to 1855. And the waves sort of rattle around inside the harbour. It takes about half an hour to get from the harbour entrance out through to the CBD and to Petone. So it does take some time to disperse within the harbour. So this is the CBD area, and our first wave comes after about half an hour. This model is a very detailed one. It's created by my colleague, Xiaoming Wang, and it's very unusual in tsunami modelling that he's actually put in every individual building in Wellington, so we can see the water exactly, really flowing around the different structures. And a series of waves, so it's not just one wave, but a whole series that comes roughly perhaps every half an hour. There's another surge that comes through. And the heights, these are heights above ground level. You're seeing heights of like 3-4 meters coming through the central part of Wellington. So what can we do about the hazard that this presents to us? Well, one of the most obvious things that we know is to come up with tsunami evacuation maps. So our research in this and other projects has helped to define these maps of showing people where you should get out of if you feel that long or strong earthquake. This is sort of the early one of the first of our maps for Island Bay. It's been through a couple of iterations since. And it was an initiative, a suggestion that came out of community meetings in Island Bay to paint the blue line on the road to indicate the edges of the evacuation zone. So that was a really nice example of community engagement that came up with something sort of quite practical that we could do. And people are, there's been good feedback on the blue lines as a way of being a regular reminder. People are going across there on a regular basis. It keeps the idea in their heads of, well, that's where we have to go if there's a strong earthquake. Since we're in Te Papa, it's worth talking about the Te Papa building, which was designed with tsunamis in mind. So the ground floor of Te Papa, which has the car park, and it also has walls that can be, it's designed basically to allow the tsunami to pass through it. So if a tsunami comes, it can pass through this building on the ground level, while the really important, valuable stuff is up on the higher floors, safe from the tsunami. So a rare example of engineering to protect against tsunamis. We've done quite a lot of work recently, particularly in It's Our Fault project, looking at what happens during an evacuation. What are the issues that people would face during a tsunami evacuation? So this is a model of an evacuation where each of these red dots represents an individual person. They felt that long or strong earthquake. They're trying to get to the blue line as quickly as possible. And we're looking at the flow of people. In this case, in this pilot study, we're looking at Petone, and we can use this kind of model to identify particular problems that might occur during a tsunami evacuation, and we can then talk with civil defence and think about, well, what can we do to help reduce some of those problems? So we can identify bottlenecks, places where too many people are all trying to get through the same space. And that can be something that can feed into future designs. You know, if we have limited number of footbridges over the railway and the highway, well, next time we can make sure that the footbridge is built so it's got enough capacity for the people, that kind of thing. We can identify the parts of town that have the greatest distance to go, and that can feed into thinking, well, what can we do? Can we do a vertical evacuation? Can people go up into tall buildings? Or is there anything else we can do to help people in those places that have the furthest to go? And other issues like people wanting to cross the bridge over the Hutt River, which is obviously not an ideal thing to be doing during a tsunami evacuation. So we've been doing this kind of work to try and help with evacuation planning. That was our pilot study, which was for Tony, but we've done studies now within the It's Our Fault project, essentially all around the Wellington region. The most recent one we've just finished, is in Eastbourne. And Eastbourne has some special problems that we have tried to look into. With Eastbourne, you've got like a narrow strip where all the towns and villages, where all the people are living, but you also have these very steep hills behind which are susceptible to landslides. So this is a map of showing, you know, landslide susceptibility, where landslides might run out to, and we can sort of investigate the effect that a landslide might have on a tsunami evacuation. So one of the issues, for instance, is that people evacuate and they've gone to their, but the route that they would normally take to get up into the hills has been blocked by a landslide. And so we can look, well, what are the implications of that? So I won't go through these graphs in detail, but what we're looking at here is where one particular road that takes you up to high ground is blocked, and we can see what's the impact, because the people who would have gone there will have to go to other places instead. It's going to take them longer. There's going to be more people there who need to be looked after. So we can take these kind of results and talk through with civil defence. We can talk through to the local communities, discuss what the issues are, and that's a sort of starting point to thinking, well, what's the right advice to give? What's the right thing we should be doing? So we might, for instance, say, well, if you live in Eastbourne, it's good not to just know your nearest evacuation place, but know some alternative options in case your first choice is not available because it's blocked off. It's also, very advantageous if you can get out of the house quickly, because if you've got out of the house quickly and you find where you wanted to go is no longer possible, then you've still got time to go to a different place instead. That's one example of where we've taken our scientific work and sort of bringing it down to the practical level of trying to be helpful at the community level. And that's all I've got. Thank you.
Thank you, William. I really enjoy those animations. It really hits home how prepared we need to be for a tsunami to come, and then the science turning into practical advice for emergency management in local communities is an excellent example of the great work that It's Our Fault does. So to conclude our talk portion of this evening is Dr. Xingling Ling, Dr. Xingling is a senior risk engineer at GNS Science, where he leads many programs and projects looking at the impacts that natural hazards have on the built environment, both in New Zealand and internationally. Welcome, Xingling.
Thanks for the introduction, Natalie. Tēnā koutou katoa, ko Shannon toku ingoa. Good evening, everyone. My name is Shannon from GNS. So I'm the last section of this talk tonight, and I'm excited to show you with an example and project we work with the community to use all this hazard information like the earthquake and the tsunami William and Kate just mentioned about, and work with the community how they can use this information to understand the risk and use them to make the decision. Sorry, it should be this one. And so first thing first, so why we want to do this? So from the talk early tonight, we understand from It's Our Fault program, or maybe from the project funded by other government agencies like the National Natural Hazard Commission, the Tokatuake. We've been producing many hazard information like the earthquake, tsunami, landslide, and the liquefaction for the Wellington region. So in this project, we want to work with the community to understand this hazard information and also help them to understand how they can use this information to make their own decision. And secondly, the reason we choose the Takapuai community for this case study is its unique location. So as you can see from the map, the community just sits next to the earthquake fault. So the community is prone to earthquake shaking. And also because the community also next to the Pereira Harbor, so it's likely to have some tsunami impact. And also the reclaimed land and also the stream within the community also gonna have some liquefaction risk. And on top of that, in the backyard of the community, it's likely to have some landslide risk as well. So because it's unique location, we choose this as our pilot case study for this project. And in addition to the unique location, lastly, and the most important reason we choose Pereira because the community is quite engaged and they support our project. So we want to thank the Takapuai community and whānau to work with us and contribute your time and effort. So what we try to do, so we want to use all this available hazard information and to quantify the impact to the people, building, and the infrastructure in the community. And the way we try to do is first we want to collect all the information and work with the community to understand what they need. And we're gonna deliver some output they're gonna use and to support their own decision. So in the rest of the talk tonight, I will quickly walk you through the methodology we use to calculate the impact, and also gonna show you some tests we do and work with the community during the project duration, and also gonna show you how the output gonna looks like. So for the methodology, the way we try to calculate the impact to the community, the first thing is we need to understand where is the building, where is the infrastructure, the water, the road network, and also where people live. So we work with the community to collect all this information. And with the people and the building infrastructure information ready, the next step for us is to collect all the available and the latest hazard information from earthquake, tsunami, landslide to liquefaction. And once we have these two information together, then we can just overlay them together. So from here, then we can identify the affect building and also the people live in the building. And of course, we also gonna calculate the impact to the infrastructure as well. So in addition to all this technical work, one of the very important activity in our project is the Hui engagement. So to make sure we develop the useful information to the community, and also the community can use them for their own decision. During the project duration, we do have many Hui with the community. From the very beginning, we discuss our idea with the community, and we co-design the project together. And we also work together to collect all the mission information. And in the end, when we have some output, we also work with the community to review the output and see the feedback from them to improve our stuff. So here is just some select image to show how we work with the community during the last year for this project. And for the following few slides, I will quickly walk you through some project activity we had during the project duration and also show you some output. So the first test we have is to collect the data. So as I mentioned previously, we first need to understand where is the people, where is the building, and where is the infrastructure. So we first collect and review all the available existing information from State New Zealand and from links or OpenStreetMap, or maybe for the Sri water, we get that from the Wellington water data set. And then we work with the community funnel to fill the gap. So we have some street survey to collect how many people live in each household and the age band and the gender to improve the data quality. And in addition to this typical data collection, during this project, we also work with the community to have some rapid assessment because the community have some funding from the government to locate the emergency container during the emergency. So we work with the community to identify the best location to place this container. So I will show you more detail about this one later. Oops. So after all this activity, here's the output for the people, building, and infrastructure asset we produce for this project. So for the building asset, in addition to the residential building, we also identify some key facility like the Malay, the school, the child care, and also the vulnerable group, for example, the social and the communal housing. And for infrastructure, we do cover the street water, the stormwater, wastewater, and the potable water. And as mentioned previously, we also help the community to identify the potential site for the emergency container. So we also put that in the map to help the community for their communication and discuss with among the community funnel. So this output will be used for this project, but we also provide this output and the map to the community so the community can use that for their future use, for example, for their future community planning and all other purpose. And so once we have all the building infrastructure and the people information ready, the next test for us is to collect the latest hazard information. So in this project, we do consider multi-hazard from earthquake. So for earthquake, from earthquake, tsunami, liquefaction, and landslide. And for earthquake, we get all the latest earthquake information from the National Seismic Hazard Model. And for tsunami, we get all the latest information from a study did for Pereira back in 2019. And for the liquefaction and landslide, we kind of build on existing map, but we do update and improve them through the recent field survey. And lastly, for the landslide, we consider both earthquake-induced landslide and also the rainfall-induced landslide, as we see recently in Cyclone Gabriel. And so with all the hazard information and the building infrastructure information, then the next step for us is to do the impact assessment. So from this project, we do produce 30 impact assessment and the map. And so let me show you. So all this map is available in this kind of poster size. So the reason we do this poster size because they're gonna help the community to do the communication, education, and risk awareness. Discuss with the funnel. So here is just some 4 examples show how this map looks like. So each of them represent different hazards from the landslide, liquefaction, tsunami to earthquake. And from this map, we can easily identify the potential affect area from different hazards in different scenarios. And in addition, we also have a table we call impact table to detail the impact to people, to building, and to street water and the road. So people can have this information to support their own decision making. And so in addition to the map, we also provide a science report. And here is just a quick summary how the impact, the multi-hazard impact looks like. So for us, quite unfortunate because we are in Wellington, so pretty much all the building and people gonna affect and exposed to earthquake shaking. And for tsunami, we expect it's low when the tsunami is caused by the 500 or 1,000 year return period period tsunami. But if we're talking about the extreme tsunami event, like the return period for 2,500 years, we will see some impact to the building in the waterfront area. And for liquefaction, in our model, we estimate about 10% of the building and also 20% of the infrastructure was going to be in a high liquefaction area. And for landslide, the assessment show us is a low risk, but we do have around 10% of the area sit in a moderate liquefaction landslide risk area. Oops. So in addition to the impact assessment I show you in the screen, also in the map, as I mentioned previously, we also work with the community to do some additional assessment. The first one is the emergency container, as I mentioned previously. So we work through the community to identify 4 potential sites for community to place their emergency container in the future. And the other additional test we did and work with the community is to assess the hazard on the uphill side, because the community is thinking about to relocate the community away from the tsunami and the liquefaction area. So we try to assess what's the likely impact if they move to uphill. So obviously, when the community move uphill, they can be away from the tsunami and the liquefaction, but that also means they're gonna increase some risk due to the landslide. So we suggest maybe the community needs some maybe more specific assessment before they make the final decision. Okay, so I think that's, pretty much me a quick summary of what we did and work with the iwi Maori community to improve their understanding of risk and also enhance their community resilience. That's me, thank you.
Thank you, Shenling. Now we'll move on to the question and answer portion of the evening. It's an opportunity for us to hear from the audience and a little bit for you to hear a bit more about what's going on. We don't actually have a lot of time left in our session tonight to do question and answers, but we will try and get the mic around. Please put your hand up if you've got a question and wait for the mic to reach you before asking your question for our audience online. So, you see, just want to...
Thank you. My name is Peter. I'm a construction engineer, so sorry about the husky noise. I just want to talk about, firstly, a question to William. Your logo shows a breaking wave, which is pretty horrific. But as I understand it, it's more a slow rise in the water levels within Wellington Harbour. So, firstly, which is correct?
So, I mean, a tsunami can, depending on the circumstances, either look like a quite steep-fronted breaking wave, or it can come up like a steady rise and fall. I think within Wellington Harbour, in those animations, it's probably more like a fairly steady, strong rise and fall rather than a big breaking wave. But both things are, in general, possible about tsunamis.
Okay, well, thanks for that. So, a number of years back, 4 or 5, there was a tsunami warning exercise where all signs went off, and most of Wellington's office community headed to go up Woodward Street, and they should have stayed put in their high-rise buildings, because I don't think a tsunami is going to knock a high-rise building down. And so, do you think there should be more education about that for the central city occupants?
Yeah, that's a good point, and there's a lot of discussion around, you know, what advice to give to people in high-rise buildings. Is it fine for them to be above a certain floor? I think Wellington City Council sort of say that a 4th floor and above is a suitable place to go. I mean, there are complicated issues. If you're in a high-rise building and a real tsunami comes through and it causes a great big mess around you, you could be trapped there for quite a long time. It's not necessarily a nice place to be. On the other hand, there's limited capacity for people to go up and down the streets to get to You know, if everybody tries to get up and through the narrow passageways up to the terrace, we can have, you know, a traffic jam of people. And other factors like, you know, if there's been a strong earthquake, you may have falling glass coming off of buildings. So that's another reason why, you know, it can be good to stay within the building. So there's complicated different factors, but it's certainly, you know, good to point out that vertical evacuation is one of the options that should be considered. Yeah.
Thank you. And since I've still got this microphone, one more question. Our earthquake codes ask us to design buildings with a risk to life of 1 in 1 million in a year. It's a micromort. So in my case, I've lived through 80 micromorts, or the risk of dying. There's an 8 millionth of a chance of me in an earthquake, in a building, which is a very, very low percentage. And then when you start to apply that to old buildings, which we engineers grapple with, and the fact that you guys are going to crank up the earthquake loading, possibly, then we seem to be dealing with very small risks when other risks should be considered in more detail, and they're numerous. And I've had enough thinking.
I mean, I for sure agree that we should be thinking both about the seismic risk and the tsunami risk to buildings, and the right way to engineer for both of those hazards together, because sometimes the things you might do for earthquake protection of a building are not necessarily helpful for the tsunami protection and vice versa. So we really do need to sort of think about those things in an integrated way.
We can have one more question.
My name is Peter. I have a question which might be highly relevant as the last question. You've been talking about the research that you are currently doing. I would understand that it also depends on research that's been done previously, decades, in fact nearly a century ago, 1855 data. What's the future?
Great.
And the reason I'm raising that question, just to make it very clear, science funding.
If I can speak for the It's Our Fault program for starters, is that we've just started a 3-year program and that's all secured. So we'll be continuing to do work for at least 3 years. Beyond that is a little more uncertain, that is for sure. Yeah, and we, as you say, the It's Our Fault program pulls together research being done in a lot of other programs. So yeah, some of that is a bit at risk.
The Wellington Collaborative is quite great because it brings together other major research programs like work being done in Quake Core, which is a research excellence core. So, and Resilience to Nature's Challenges, which is wrapping up, but there's things on the horizon there as well. So it's really great that the enduringness and the longevity of It's Our Fault is continuing to go on, and we're going to continue to support it and bring together all these other pieces of research that's been happening across the programs. So we have run out of time. Thank you Te Papa for letting us stay a little bit longer. And thank you to those who have joined us online as well tonight. Before we go, I'd just like to remind you about their last talk in this series on Tuesday, the 28th of August. We'll hear how research centred in Te Ao Māori is contributing to New Zealand's resilience planning. So now I'll hand it back to Kate to close us off with a karakia and how to exit.
So I just wanted to reiterate a huge thank you to tonight's fantastic speakers, Nicola, Kate, Shenglin and William, as well as Natalie for facilitating. Thank you for your time and generosity sharing your range of research. We really appreciate you being here tonight. We'd also like to thank the Natural Hazards Commission Tokatu Ake, one of Te Papa's founding partners who've supported us for over 25 years with our exhibitions and education programme. Thanks to their generous funding, through partnership, we are able to connect museum visitors, tamariki, rangatahi with vital information about Aotearoa and New Zealand's hazards, natural hazards, and how to be prepared. And Natalie's already done my job fantastically. Please join us again in a couple of weeks if you would like to hear our final talk in the series, or if you're unable to join us in person, these will be live streamed and found online. So I'm going to close this evening with our final karakia. E rongo, ko te rongo a whare, ko te rongo a marae, ko te rongo a te hā, ko te rongo mai whiti, kia hau mai ko te maungarongo, ko te rongo mō, e rongo. Whakairia ki runga, kia tina, haumie, huie, tai kie. Thank you and get home safely.